Dear audience, it's a pleasure to present this paper, Multiscale Approach to Fatigue Crack Propagation Paths in Cold Drawn Pearlitic Steels. For author Jesus Toribio, myself, Beatriz, Gonzalez, Juan-Caros, Matos, and Francisco-Javeier Ayaso. We are with the Fracture and Structural Integrity Research Group of the University of Salamanca. Beautiful logo and 800 years old. The oldest in Spain and one of the 4 oldest in Europe. The outline of my presentation into 5 parts: introduction, experimental procedure, experimental results, discussion, and conclusions. Introduction. Motivation, scientific interest, the study of the macroscopic fatigue performance of eutectoid steels and its relation with the microstructure. The importance of the study to analyze how the cold drawing process influences the fatigue microdamage in pearlitic microstructures. The aims of the work: the study of the fatigue behavior of progressively drawn eutectoid steels, analyzing in particular the effect of progressive cold drawing on the crack aspect ratio evolution and the fatigue macrocrack path, and the effect of progressive cold drawing on the fatigue crack path at the microscopic level fatigue microcrack path. Experimental procedure: pearlitic steel with eutectoid composition, 0.8% of carbon, from hot roll bar 0 drawing steps to cold drawn wire 7 drawing steps. Microstructure: in the hot roll bar, left hand side green color, randomly oriented microstructure in both longitudinal and transverse direction, and in the cold drawn wire, randomly oriented and fully packed in the transverse direction, decrease of interlamellar spacing and curling, and markedly oriented in the y-axis or cold drawing direction after cold drawing in the longitudinal section. The evolution of stress-strain curves with a clear improvement of mechanical properties, yield strength and UTS, as a consequence of the drawing process, as an increase of the cold drawing process. The testing procedure, axial fatigue test in a universal testing machine, to look for the macrocrack paths by optical microscopy and the microcrack paths by scanning electron microscope fractometallography. Summary of experimental results regarding macrocrack paths: left hand side green color hot roll bar, right hand side red color cold drawn wire. Both hot roll bar and cold drawn wire exhibit an elliptical crack front evolution, but regarding macrocrack paths for intermediate degree of cold drawing, the steel wires exhibit retardation in the central area. This is 1 drawing steps in green and 6 drawing steps in red. This retardation in the central area of the crack front due to the presence of compressive residual stresses in that zone. It's a kind of Gill effect. Regarding microcrack paths, in green color left hand side hot roll bar, red color, orange color in the right hand side cold drawn wire. Similar fractographic appearance of the crack path, microplastic tearing for different drawing degrees. The fatigue surface reveals a topography with striations in the microcrack path, and secondary microcracks on fatigue surface, local deflections, branchings, bifurcation also appear. In the microcrack paths, this is the corresponding to the fully drawn material, we have zigzag microcrack path with local micro deflections. This is a summary of microcrack paths in the hot roll bar, green color top, and cold drawn wire, orange-red colors, bottom of the slide. We can see the results of microcrack paths for different levels of stress intensity range. The heavier the loading, the greater the stress intensity range, the more tortuous the crack path. This is expected, and with regard to the influence of the drawing degree, it produces an increase of micro deflections, an increase of the micro deflection angle, and an increase of the frequency of deflection, bifurcations, and branches. As a summary of microcrack path, we have an increasing number of microdeflections with shorter branch microlength and higher microdeflection angle as a consequence of the cold drawing process. An increase of the real fatigue fracture surface, a decrease of the fatigue crack growth rate, microstructure-induced fatigue crack growth retardation, and drawing-induced fatigue crack growth retardation. Discussion. With regard to microcrack path and the Gould effect, after finite element analysis, we observe that the cold drawing process produces an axisymmetric residual stress profile. Here we represent radial, hoop, or annular and axial residual stresses, and these axisymmetric residual stress profiles contains compressive residual stresses at the center and tensile at the border, thus influencing the fatigue crack front shape. Microcrack path resembles microdamage. The fractographic appearance resembles microplastic tearing, which is consistent with fatigue damage and crack advance developing by accumulation of plastic strength. With regard to microcrack path, we have the hot roll bar green color in the left-hand side and the cold round wire orange color in the right-hand side. Fatigue cracks are transcolonial, they cross the colonies, green color, and translamellar, red color. It is the crack path crosses the colonies, green, and breaks the lamella, red. The main crack exhibits a non-uniform COD, yellow color, and micro discontinuities. Secondary cracking appears in the forms of local deflections, branches, and bifurcations in yellow color. Cold drawing process produces a microstructural orientation, microstructural elongation of pearlitic colonies and lamella in the cold drawing direction. With regard to this multi-scale approach to the fatigue microcrack path, here we have an schematics of the microcrack path in both the hot roll bar, green color left, and cold round wire, orange red color right. We observe that D7 lower than D0, that is, the length of the micro branch is smaller for the fully drawn material. However, the micro deflection angle, theta 7, is higher than theta 0, that the micro deflection angle of the hot roll base material, which is not cold drawn at all. Then fatigue microcrack path in the cold drawn wire exhibits more deflections and with higher angle. Even they are shorter but with higher angle. As a consequence, we have a retardation of fatigue crack propagation. Multiscale approach. The key microstructural unit could be the pearlite colony. Here we have a colony with common orientation of ferrite cementite lamella, a colony with pearlitic lamella parallel to each other, and an enlarged colony after drawing direction in vertical side. Then we have a decrease of interlamellar spacing, S7 lower than S0, and an orientation, an increase of angle of orientation of the lamella and of the colonies. As a consequence, in the microcrack path, hot roll bar, left-hand side, green color, and cold round wire, fully drawn material, orange red color, right-hand side. D7 lower than D0, the length of the micro branches is lower as in the fully drawn material, but the micro deflection angle is greater in that fully drawn material. Again, with this multi-scale approach, the key microstructural unit with decrease of interlamellar spacing and orientation in the drawing direction of both levels, and regarding microcrack path, small branches but greater microdeflection angle, the key microstructural unit governing the fatigue crack growth is the pearlite arrangement, The key parameters being both the interlamellar spacing and the pearlitic plate's orientation, since the ferrite-cementite interface block the dislocational movement, thereby producing a local retardation of the crack propagation. The micro-crack path deflection, we observe changes in cracking direction which are frequently associated with changes in pearlitic lamellar orientation of different colonies. Possible explanation, dislocational movement in ferrite lamella between cementate plates that block the glide. Here in yellow we have the colonies with different orientation of lamella and the cementite lamella blocking the dislocational movement which is possible in the ferrite more ductile sheet. And let's go to the conclusions. 1. Fatigue crack propagation in interthreaded steel wires under tensile loading in the Paris regime develops in mode 1 with an elliptical crack front. The steel wires with an intermediate cold drawing degree exhibit a retardation at the crack front center due to the presence of compressive residual stresses in the central area of the crack front. Gould effect. The cold drawing manufacturing process improves the fatigue performance of outlet steel by retarding the fatigue crack growth rate in the Paris regime. The fractographic appearance of the fatigue cracks resembles microplastic tearing, which is consistent with fatigue damage and crack advance by accumulation of plastic strain in the vicinity of the crack tip. From the microscopical point of view, the fatigue cracks are transcolonial and translamellar. It is, the fatigue crack path crosses the colonies and breaks the lamella. The crack opening displacement is not uniform along the crack, and many micro discontinuities, branches, bifurcations, and local deflections appear, the latter especially in heavily drawn steels. Thus, the cold drawing process produces a tortuous crack path, so that the higher the cold drawing degree, the more tortuous the crack propagation path, the microcrack path. The key microstructural unit governing the fatigue crack growth is the pearlite arrangement, the key parameters being both the interlamellar spacing and the pearlitic plate's orientation. Since the ferrite-cementite interface block the dislocational movement, thereby producing a local retardation of the crack propagation and the tortuous crack path. And with the logo of my university, the beautiful logo of the University of Salamanca, that's all. Thank you very, very much for your kind attention.